Junction field effect or transistor construction. Major part of the structure is the N type of material is the N channel for the JFET. Top end of the N channel is connected to a ohmic contact is the drain terminal. Bottom end of the N channel is connected to another ohmic contact is the source terminal. That is, this one it is a drain terminal, this one it is bottom terminal, that is the source terminal. P type of materials are embedded at the two sides of the N channel. That is P type of material. Here this one it is a P type of material, here it is a P type of material. These P type of materials are embedded at the two sides of the N channel. P type of materials are connected to ohmic contacts is the gate terminal. These two P type of, this one P type of material, here it is also P type of material, and these P type of materials are connected to ohmic contacts, that is here ohmic metallic contact is a gate terminals. Two PN junctions are present in the JFET. Here one is the PN junction and this one is another PN junction. Two PN junctions are present in the JFET. Two depletion regions are developed at the JFET. Here one depletion regions and here it is also another depletion regions are developed at the JFET. The depletion region is wide of free carriers. That is, wide means these are the empty of the free carriers. So that this does not support the conduction of the current. Since these depletion regions are empty of the free carriers, so that does not support the conduction of the current in the depletion regions. Operation. When the gate to source voltage is equal to 0 and drain to source voltage greater than 0 is applied. The gate is connected to the source terminal. Gate terminal is at ground potential. Here source it is connected to ground and gate it is also connected to the source, so that the VGS, the voltage between gate and the source, it is equal to 0 volts, is at the ground potential. The biasing voltage VDS is applied between the drain and the source terminals. Here this one VDS it is applied between the drain and the source terminals. Under the unbiased conditions, the VGS is equal to 0, VDS is equal to 0 and ID is equal to 0 amperes. If we not apply the any voltage, biasing voltage VDS, so that VGS is equal to 0, VDS is equal to 0 and ID is equal to 0 amperes. As VDS greater than 0 is applied, the electrons starts to move from source towards the drain. Electrons starts to move from the drain towards the source. The width of the depletion regions at the both sides of the channel increases. The width of the depletion regions at the both sides of the channel increases. Here the drain current ID increases as the VDS increases. The drain current ID increases as the voltage applied between the VDS it is increases. The width of the depletion region at the drain end of the channel is more as compared to the source end. Here the one thing that is to be noted is that the width of this depletion regions. Here the depletion regions, these are extending in the channels, and as VDS increases, the width of the depletion regions at the drain end of the channel increases. As compared to the source end of the channel, the a reverse bias voltage is developed at the drain end reverse bias voltage developed at the drain end is more as compared to the source end. Here, whatever that reverse voltage which is applied in, whatever the reverse voltage which will be applying to between the drain and the source, due to which the reverse bias voltage developed at the drain end is more as compared to the source end. The magnitude of applied voltage VDS is increased. The width of the depletion regions at the drain end goes on increases. The width of the depletion regions at the drain end goes on the increases. At the particular value of VDS, both the depletion regions extending in the channel, touch each other. Both the depletion regions extending in the channel touch each other. This condition is known as the pinch off. This condition is known as the pinch off. The voltage VDS at which this pinch off occurs is known as the pinch off voltage VP. This condition is known as the pinch off. This condition is known as pinch off. The voltage VDS at which this pinch off occurs is known as the pinch off voltage VP. As VDS increases, drain current ID also goes on increases. At pinch off, drain current is not equal to 0 but is reduced to its saturation value IDSS. At the pinch off, the drain current is not equal to 0. The drain current ID at pinch off, drain current ID is not equal to 0 but is reduced to its saturation value, that is the IDSS. Here, as this is the figure at which we shall know about the operation of the how that pinch off occurs in the JFET. When VGS is negative, as negative voltage of VGS increases, the voltage VDS at which pinch off occurs, goes on decreases. The voltage VDS at which pinch off occurs goes on decreases. The saturation current of ID, that is IDSS, also decreases. Due to which the drain current ID also decreases. As VGS becomes more negative, as the negative value of the VGS is increased, more negative, at a particular value of VGS is equal to minus VP, that is pinch off voltage, the drain current ID is equal to 0 amperes. So that the VI characteristics of drain current ID versus drain to source voltage VDS for VGS as a parameters are shown in the figures. That is the drain current versus the drain to source voltage as VGS for different values of VGS as a parameters are shown in the figures. Here the VI characteristics of a JFET, here the VGS is equal to 0 volts. VGS is equal to, when VGS is equal to 0 volts, you have to apply the that is the drain current is more. Drain current is more because here the saturation value of the drain current increases, because VGS is equal to 0 volts. As VGS is a negative value of VGS is applied, it is equal to minus 1 volts, then the saturation drain current decreases, the saturation VDS also decreases. Again, when VGS is equal to minus 2 volts, VGS is equal to minus 3 volts, again there is a decrease in the saturation value of the drain current. When the VGS is equal to minus VP, that is pinch off voltage, the drain current almost equal to 0 volts. Drain current ID, it is equal to the, when VGS is equal to minus VP, the drain current is equal to 0 amperes, because at the pinch off current becomes equal to 0. This one it is known as the saturation region in the AI characteristics. This one it is the linear region in the AI characteristics. Here it is the cutoff regions, because here the drain current ID increases with respect to the VDS in the linear regions. But in the saturation region, the drain current, the after pinch off, that is the drain current ID, the drain current ID remains constant for the any increase in the VDS, because after pinch off there will not be any effect of VDS on the drain current. The drain current reduced to its saturation value. Here this one it is the saturation regions, and for the voltages is VGS is equal to VP minus VP pinch off voltage, that is known as the cutoff regions. Now the transfer characteristics. For BJT, characteristics between the input current IB and the output current IC is equal to beta IB. For JFET, the characteristics between the input voltage VGS and the output current ID is the transfer characteristics of the JFET. Here, there is a exponential relationship between VGS and ID, but here there is a linear relationship. Here in the BJT it is a linear relationship between the output current and the input current, but here there is an exponential relationship between the input voltage and the output current. As a negative VGS increases, the ID goes on decreases exponentially, so that here ID is equal to IDSS into bracket of 1 minus VGS by VP. IDSS into bracket of 1 minus VGS by VP whole square. This is the relationship between the input voltage and the output current. Now, one of the methods that is used to draw the transfer characteristics, that is the shorthand method to draw the transfer characteristics of the JFET. Here this one it is VGS, here it is ID. So that here when ID is equal to saturation current and VGS is equal to 0, ID is equal to IDSS, because here in this equation, according to this equation, shall write here that when VGS is equal to VP, ID is equal to the IDSS. Now when the if you reduce ID from IDSS to IDSS, half of the IDSS, then if you put this equation, it is equal to 0.3 pinch off voltage. And when the drain current reduces to IDSS upon 4, it is the VGS, it is equal to the half of the pinch voltage. And when drain current ID is equal to 0, the VGS is equal to the pinch off voltage. According to, if you put all these parameters, we will get the other parameters from this equation. From the this is the one of the equation. Now from that one, here you will be getting transfer characteristics. This is the drain current, here it is the gate to source voltage. Since we are applying for the N channel JFET, a negative VGS is applied, so that we will be getting in the second quadrant in the characteristics. Sketch the transfer characteristic curve defined by IDSS is equal to 12 milliampere and pinch off voltage is equal to minus 6 volts. According to the shorthand method to draw the transfer characteristics, here this one VGS and here it is ID. So that first one, that is when VGS is equal to 0, we will be getting the ID is equal to IDSS, and when VGS is equal to, that is 0.3 VP, 0.3 VP ID, you will be getting the half of the saturation current, and when the VGS is equal to 0.5 VP, that is the, here this one it is 0.5 VP, here it is 6 volts and here it is 3. Now the drain current ID is equal to 3 milliamperes and VGS is equal to 6, ID is equal to 0 milliamperes. Okay. Now from the calculated values of drain current and gate source voltage, shall draw the transfer characteristics for the given JFET, so that here IDSS upon 2 and here it is the VGS, and here IDSS upon 4 and here it is the VGS, so that Here, if we join all these parameters, that is here VGS is equal to pinch of voltage VP, and here ID is equal to IDSS at this point. So from these equations, if we got these 2 points, if we join all these points in the second quadrant, you will be getting the transfer curve for the given JFET. Now, depletion type of MOSFET. That is a depletion type of n-channel MOSFET construction. A p-type of substrate is formed from a silicon slab. A p-type of substrate is formed from a silicon slab. Substrate is present within the device, but in some type of the, here this one it is a p-type of substrate, and here this one it is formed from a silicon slab. Substrate is present within the device. Substrate is present within the device, but in some type of the in some type of devices, substrate is connected externally. Drain and source terminals. This one it is drain, and this one it is the source. Drain and source terminals are connected to the N channel. Drain and source are connected to the N channel. Drain and source terminals are connected to the N channel regions in the substrate through a metallic contacts. Drain and source terminals are connected to the N channel, are connected to the N different regions, N diffused regions in the substrate. Here, these are the diffused regions, N diffused regions in the substrate through metallic contacts. Through the metallic contacts, the N channels are connected. The N-channel gate terminal is connected to the metallic contact, which is the N-channel gate terminal. Gate terminal is connected to the metallic contact, which is insulated from the N-channel by a layer of silicon dioxide. Here, gate terminal is connected to the gate terminal is connected to the metallic contact, which is insulated from the N channel by a gate terminal is connected to the metallic contact, which is insulated from the N channel by a layer of silicon dioxide. The high input impedance of the MOSFETs is due to the insulating material silicon dioxide between the gate and the N channels. Here, the high input impedance of the MOSFET is due to the MOSFET is due to the The high input impedance of the MOSFET is due to the insulating material between the gate and the N channels. Now operation. And the VGS is equal to 0 volts, VDS greater than 0 volts. Here a voltage VGS is applied between the gate and the source, and a voltage that is the operating principle. Here this one it is a MOSFET, here it is the N channel, and VGS is equal to 0, VDS greater than 0. Here it is the N channel, N diffused regions in the N channels, so that gate drain source. The positive terminal at the drain, positive potential at the drain terminal attracts the electrons in the N channel that forms the drain current ID, which is when VGS is equal to 0 and ID is equal to IDSS. When VGS is equal to negative voltage is applied between the gate and the source terminals. The negative voltage at the gate terminal attracts the holes from the P substrate, the electrons in the N channel. A negative voltage is applied between the gate and the source terminals. The negative voltage at the gate terminal attracts the holes from the P substrate. The electrons in the N channel recombine with E is the negative voltage at the gate terminal attracts the holes from the P substrate. The electrons in the N channel recombine with the holes moved from P substrate to the channels. That is, the electrons will move from the move from that the diffused region, so that these will move from that to the P substrates, and similarly a positive potential at the N channel attracts the holes. The P substrate, the electrons in the N channel recombine with the holes moved from P substrate to the N channels. The number of electrons is chosen. The number of electrons in the channel decreases, the drain current decreases, so that from the P substrate, the electrons in the N channel recombine with the holes and moved from P substrate to the N channel. The number of electrons in the channel also decreases, drain current decreases at the magnitude of the negative voltage. The increased the recombination in the channel increases, the drain current ID also decreases, so that at a particular negative value of the VGS ID becomes equal to 0. That value is known as VGS is equal to minus VP. It is equal to ID is equal to 0. The characteristics, VI characteristics of a JFET. Here this axis y-axis it is for the drain current id is equal to milliamperes, and this one vgs is equal to vp. The transfer characteristics is the relationship between the input voltage the input voltage and the output current is id is equal to idss into bracket of 1 minus vgs by vp whole square. The shorthand method is channel number, it is easy, so that ib the shorthand method is to transfer the characteristics can be drawn. The shorthand method transfer characteristics shorthand method transfer characteristics can be written as id jft ids upon 2 vds upon 2 ids. IDSS is equal to 12, Vp equal to minus 12, so that from that shall draw the by using these equations the first shall determine these values from the whatever the information given by the given to the this. IDSS here it is 0. From that equation, Shockley equation, 1 minus VGS by VP whole square. VGS it is equal to 0. Here 12 milliamperes and here it is the 6 volts. From the given data, here the VGS is equal to 0, it is 12 milliamperes, and VGS is equal to 1.8. VGS is equal to 1.8. The IDSS it is equal to 3 volts. And VGS is equal to 3 milliampere. 3 milliampere ID is equal to IDSS upon 4, it is equal to the 3 IDSS upon 4, it is equal to 3 is equal to 3 milliamperes, and so the VGS is equal to 6, ID is equal to 6. Enhancement type MOSFET construction. Substrate is of a P type of metal from a silicon slab. Substrate is connected in terms to the source and substrate is connected internally to the source in some of the devices, but in some the substrate it is connected outside, but in some it is connected internally, so that the connected externally. Drain end of the source terminals. Drain end of the source terminals are connected to the n different channels. The drain and source terminals are connected to n diffused regions through the metallic contacts. Gate terminal is separated from the P substrate by an insulating layer of silicon dioxide. Here, this one it is a insulating layer of silicon dioxide, so that the no channel is present between the two n diffused regions. The no channel is present between the two n diffused regions, so that the characteristics also it will be different for this device. No channel is present between the two n diffused regions. Gate terminal is separated from the P substrate by an insulating layer of silicon dioxide. Here this one it is a silicon dioxide layer, and this silicon dioxide layer this will separate the gate terminal and the that is the gate terminal and the source. Here the no channel is present between the n diffused regions. Operation: when VGS is equal to 0 volts, VDS greater than 0 volts, two reverse biased junctions in the P substrate, no movement of carriers between the diffused regions, and drain current is equal to 0. No movement of carriers between the n diffused regions, and drain current is equal to 0, and VGS is equal to 0 volts and VDS greater than 0. And VGS is greater than 0, VGS it is the greater than 0, the positive voltage at the gate attracts the electrons from the P substrate. The positive voltage at the gate that will attract the electrons from the P substrate and the P substrate, and pressure the holes near the silicon dioxide layer to move deeper into the P substrate. Gate attracts the electrons from the P substrate and pressure the holes near the silicon dioxide layer to move deeper into the P substrate. The region near the insulating layer is wide of free carriers, so that the electrons from an insulated region, the electrons from an induced region near the insulating layer The electrons form an induced region near the insulating layer. At this point, the electrons form the insulating layer near the insulating layer. Form an induced region near the insulating layer. As the magnitude of VGS increases, at particular value, carriers move in the induced regions. At the particular value, as the magnitude of VGS increases to a particular value, carriers move in the induced region from source towards the drain. The drain current ID increases. The value of VGS is known as the threshold voltage VT. The value of VGS is known as the threshold voltage VP, and the carriers move in the induced region from the source. Carriers move in the induced region from source towards the drain. Drain current ID increases. This value of VGS is known as the threshold voltage VT. VGS is equal to the VT. If VGS is maintained constant and VDS is increased, the drain current ID increases initially, then remains constant and reaches to its saturation value IDSS. As the magnitude of VGS decreases, the saturation value of VDS decreases. The drain current also decreases. So that VDS is equal to VGS minus VT, ID is equal to K into bracket VGS minus VT whole square. As VDS increases and VGS is maintained constant, according to the relationship VDG is equal to VDS minus VGS, the width of the depletion layer at the drain end of the induced region is more as compared to the source end. At a particular value of VDS, the depletion region touch the silicon dioxide. At particular value of VDS, the depletion region touch the silicon dioxide layer. That is known as that is pinch off occurs. The drain current ID reaches to its saturation value and remains constant. Here see how the characteristics will be getting. Drain current ID in milliamperes, VDS it is in volts, so that here when VGS is equal to VGS, it is equal to high voltage plus 8 volts. Drain current ID it is in milliamperes 1, 2, 3, 4, 5, 6, 7, 8. VDS it is in volts 5, 10, 15, 20. VGS here the width of the depletion region at the drain end of the induced region is more as compared to the source end, so that at a particular value of VDS, the depletion regions touch the silicon dioxide layer, pinch off occurs. ID reaches to saturation value. Here, this one. Here you will be applying VGS, it is maintained constant, and here this one it is VDS. Here the at the drain end of this induced region between the drain and the source, this touch the this region that is touch source, and at the particular value of VDS the depletion region touch the silicon dioxide layer. Here this depletion region touch that silicon dioxide layer at the drain end, so that the drain current it remains constant, so that the here one thing is that at saturation value IDSS, as the magnitude of VGS decreases, the saturation value of VDS also decreases. Here this one here as the plus 8 for the high value of this VGS will be getting the values. Here VGS is equal to 8 volts, so that it is goes on increasing, and after that here a pinch of occurs, the pinch of occurs, and the drain current remains constant. If the value of VGS it is reduced, then the drain current also it is reduced, because here that pinch of occurrence it is also goes on the that is as the VGS decreases, the pinch off also goes on the decreases, that is the saturation value of VDS also decreases, plus 4 volts, plus 3 volts, plus 2 volts. The value of VGS is known as the threshold voltage. VGS is maintained constant and VDS is increased, ID and then remains constant. Okay. VGS is equal to threshold voltage. Transfer characteristics. ID is equal to K into bracket of VGS minus VT whole square. K is equal to constant, VT is equal to threshold, as specified by the manufacturers in the graph of the output current ID versus the input voltage VGS gives the transfer characteristics. The graph of the output current ID versus the input voltage VGS gives the transfer characteristics. For different values of VGS, the drain current is calculated, and characteristics between drain current and gate to source voltage VGS is drawn as shown in the figure. Here the transfer characteristics of the device. So, for the difference between the depletion and the enhancement MOSFETs. Okay. The biasing of FETs, a fixed bias configurations. Here that is the one of the configuration of the FET, that is a fixed bias configurations. Here the drain resistance RD, a RG and a VGG, that is the biasing voltage is applied, a coupling capacitor C1 at the input, a coupling capacitor C2 at the outputs. The coupling capacitors for the DC analysis under the DC conditions are open circuited. The coupling capacitors which are present at the input and output are the open circuited. The input impedance is high for the FET. The input impedance is high for the FET. The gate current is equal to 0. The gate current is equal to 0, Ig is equal to 0 amperes. The drop of voltage across Rg is Ig is equal to Rg is equal to 0 volts. Rg is short circuited. Now the circuit is reduced to here. This because the coupling capacitors are open circuited under the DC conditions. So that here the gate current is equal to 0, so that the drop of voltage across this Rg it is also equal to 0, and this circuit it is reduced to here in this forms, that is a fixed voltage VGG. Here it is the voltage between gate and source VGS, drain source VDS and RD. VGS applying KVL at the input, so that minus VGS is equal to 0, VGS is equal to minus VGG. A negative voltage is applied between the gate and the source. The voltage applied at the input is fixed, so that VGS is also fixed. The voltage applied at the input is fixed. The gate to source voltage VGS is also fixed, so that this type of biasing is known as the fixed bias circuits, because a fixed voltage is